Okay, so chapter 3 of an introduction to statistical learning. This is question 10 from chapter 3. This is part of the applied questions. Here I will be coding in R, and I'll make a separate video for Python. Let's get into this. So the first thing we need to do is to install and load the ISLR package, okay, with this code block here. And we're going to be working with the Carseats data set. Okay, and so I need to load that, but I don't know much about the Carseats data set, and so I need to learn some things about it because I'm going to be using certain variables, okay, such as price, urban, and US, and I don't really know what those are. Excuse me. And I don't really know what those are. So in this block of code, I'm going to load that data set, and then by using question mark Carseats, I'm going to get some information on it, and then I'm going to see I'm going to get an outline of what the data looks like. Okay, so with this line right here, I pull up this little window over here, and it says that Carseats is a simulated data set containing sales of child car seats at 400 different stores. The variables that I'm going to be looking at are sales, and so that's unit sales, so thousands of car seats at each location of these stores. Urban price, which is just the price for each car seat that the company's charging, and then urban and US, and we see that urban and US are both factors. Okay, so they're a yes or no in both cases. They are yes and no. Of whether or not the store is in a urban location or not, and whether the store is in the United States or not. Okay, so that's what our variables are there, and I guess maybe I'll leave that up here. Okay, so part A, I want to fit a multiple linear regression on price, urban, and US, modeling sales. Okay, and so that's what I'll do here. So I'm calling it CSReg. I use the linear model function, the LM function. And my formula here is sales regressed on price plus urban plus US, and the data is car seats. I don't have any interactions here, but that's fine. The next part is to provide an interpretation of each coefficient in the model. So when I do that, or in order to do that, I need to use the summary function for that regression. So I run this. And we've seen this before. The information that we're interested in is under this coefficients table. Okay, we'll be looking at this bottom part a little bit later on, but let's provide an interpretation here. So we see that that price and US have significant associations with sales. Okay, and the estimate, well, and urban does not, apparently. And that the estimate of those associations is given here in the estimate. So for price, it's saying that that for every 1 unit increase in price, I'm not sure what a unit is, it doesn't specify it over here, it might be dollars, it might be tens of dollars or whatever, that sales go down by 0.5, okay? So remember, a unit for sales is thousands, so that would be about 50 car seats. So that would be a $1 increase in price causes 50 car seats fewer to be sold. That seems a little bit too strong for me, so I'm not sure that price should be in dollars here. But anyway, and then similarly for US, so when a store is in the US, yes. No, I don't add that. That is something that that R automatically adds, right? Because if it's a factor, there's 2 levels of it. There could be more, but here there's 2 levels, and it has to tell us which one has the estimate of 1.2. Okay, it would be a different estimate for no. Actually, well, it would be 0. There would be no estimate for no. But anyway, it says that if a store is in the US, all else being equal, that our regression predicts 1.2 more units to be sold. So that would be 1,200 more car seats to be sold. Okay. In part C, it just wants us to run the regression. Okay, so, or not run the regression, but to write an equation for the regression. So all I'm going to do is I'm going to say sales equals alpha, the intercept, plus beta price times price, beta urban times urban, okay, so on and so forth. Okay, but it says to make sure to carefully handle the fact that US and urban are factors. They're categorical or qualitative variables. Okay, I don't know the best way to signify that, but what I've done here is, so remember, urban, it's not like you have a bunch of values, 0 through 100 urban. You either are or you aren't, and so I've specified that urban yes with this underscore or with this subscript, and similarly for US. Okay. The next part is, so from our output, from our summary output, for which coefficients can we reject the null hypothesis? The null hypothesis being that beta equals 0. Okay. So what we need to do, so it depends on what our level of required confidence here is, but we look for sufficiently low p-values, and usually the low enough p-value is 0.05, and we see that that price and US are much lower than 0.05. Okay, but for urban it is not. So the ones that we can reject the null hypothesis for, which means we think that these things do have an association, are price and US. Okay. So now on the basis of what we just talked about in part D, right, the variables for which we think there is an association with price, we want to write a new regression that just uses the compelling terms here. Okay, and so again, that's going to be for price and for US. So I have in part E here, I have a new regression that I'm just truncating. Okay, so CS reg trunc. Okay, so I use the same looking code, but notice that I don't have urban as a predictor. And now part F, it asks us to compare how well the models fit the data. Okay, so now to do that, I'm again going to run summary, and I'm going to run summary for both models here. So let's just demarcate this with our eyes. So this first part is the summary for the first regression, and then the second part is the summary for the second. And the information that we want is going to be contained in this lower block, okay, here and here. And I've taken these values and put them in a table here just for ease of consumption. Okay, so some ways that we can begin to assess the fit of these models. So here I have this column is for the first regression, second one is for the second regression, and then here's a third column that says which of the two models has a better fit according to the criteria set out in the very first column. Okay, so the first one, residual standard error, right? You see that right here. Okay. So the higher the error, the less well fit the model is to the data. And we see that the first one has a slightly higher standard error than the second, and so the second model there's evidence that the second model is a better fit. Okay, and now we want the multiple R squared, right, which is here. And so for the two models, it's the same, and so I'm going to say that it's a draw. Okay, but I'm going to come back and expand on that in just a second. So remember that with the fit of a model, generally, not in all cases, but generally, as you add more terms to the model becomes more flexible and therefore tends to fit the data better, yes. But we can add too much complexity, in which case that fitting to the data becomes overfitting. In other words, the model will not generalize very well to other sets of data that came from the same source, right, from wherever we got our sample. All right, and so in other words, the more predictor variables that we have in a regression, we should expect it to fit better, but not necessarily because it's a better representation of the data, right? Not that it will generalize better to other data sets, but just because the model is more flexible and therefore may be overfitting. Okay. So one way that we can handle that is to also account for the number of predictor variables that we're using, and that's what adjusted R squared is doing here. Okay, so in the adjusted R squared, right, we see that the second model has a higher adjusted R squared, right, which means it's accounting for more of the variance in the data. So it would be a better fit. Okay. Now if we take what we just learned and applied that to the multiple R squared, which is not accounting for the multiple parameters, but we know that the first model has more parameters than the second, and yet they have the same R squared value, right? Which suggests, so generally we would expect the first model, having more predictor variables, to have a higher R squared, but it doesn't. They're equal. And the fact that the second one is a simpler model but has the same R squared value suggests that really this might not be considered a draw, but that the second model is doing better. Okay. And then the last one we might use is the F statistic, as well as the p-value associated with the F statistic. The higher the p-value, the better the model is doing at fitting the data roughly, and we see that the second model has a higher p-value. Okay, or I'm sorry, a higher F statistic, similar p-value. Okay, okay. Part G, we want to where's part G? We want to find confidence intervals for the coefficients in this second regression. So I can just use the conf_int argument. Okay. And so I get confidence intervals for each estimated parameter, the intercept, the beta price, and the beta US. Okay. And this is what they are. This is a 95. I've set the level at 95%. Okay. So we get the two boundaries for these confidence intervals. Now notice that that 0.95 is 1 minus the significance value for our p-value, which is 0.05, right? And so there's a symmetry here. So so at a level of 0.95, if a coefficient is going to be significant, it will not cross 0, right? So this is below 0 and this is below 0, right? This is above 0, this is above 0. Okay? And both of these have significant p-values. Okay, so a significant p-value to a p equals 0.05, right? Its confidence interval at 1 minus 0.05 will not cross 0, right? And that's what we see here. So the fact that this doesn't cross 0 and this doesn't cross 0 is completely compatible with the fact that these are both significant findings. Okay. And then finally, we want to look for evidence of outliers or high leverage observations in the model from E. And so there's a lot of ways of doing this. And so what I am going to do is I'm going to plot a particular diagnostic plot, which I'm selecting with which. Actually, let me just run this really quickly. So when I run plot and then the model, I get all sorts of diagnostic plots, right? I get a bunch of them. But the one that I want is actually number 5, okay? So I'm going to run number 5. And number 5 is looking for, is mapping leverage and residuals or standardized residuals, okay? And so we can look for high residual points, okay, out on the x-axis, and we see one that has more leverage than the others. I don't know that it's necessarily a high leverage point, but it's higher than the others, and maybe a few other moderately high values, okay? So that's one thing, but just because something is high leverage does not mean that it is an outlier necessarily. It has to also have a large residual, very high or very low here, and the high leverage point does not, and these moderately high leverage points don't seem to have crazy residuals, right? So these are also not. I don't know that we would consider these outliers, but anyway, this is how we would begin to go about finding outliers and high leverage points. Okay, thanks.